This is the Mirage faster than light communication protocol. Here is the communication setup. We would begin with a laser that emits 405 nanometers, enters beta barium borate crystal. Exiting are two entangled streams of photons, both at 810 nanometers. They are entangled and in a state of superposition regarding their axis of polarization. I've drawn 3 time spheres here. Time 1, time 2, time 3. This is the receiving arm, and this is the arm we will manipulate in order to receive a signal over there. The measuring device, which I'll cover shortly, is always positioned at time 2. And the manipulation device on this arm is alternated between time 1 and time 3, either before this is measured or after this is measured. The manipulation device is a polarizing, beam-splitting prism, where photons enter. Horizontally polarized photons go one way to a beam stop. Vertically oriented photons go the other way to a beam stop. If we measure on this arm, before the measurement occurs here, the output will be no interference pattern. If we measure after the measurement here, the output will show an interference pattern. Now, if you're saying, stop, you're wasting my time, people have tried this before, then you are at the right spot. You know enough to appreciate the subtlety and beauty of what I'm about to show you. First, answer me this riddle. There are 2 experiment setups here. They are very similar. I will go over them, but let me capture. There are key points. The key point is that this upper experimental setup has 2 separate inputs, 2 separate laser beams. This input has 1 laser beam. Both of these experimental apparatuses have an output of an interference pattern. Let me go over the elements here quickly. This is a polarizing beam-splitting prism. This is a beam stop. This is a mirror. This is a mirror. This is a half-wave plate, which means that if photons entering are vertically polarized, they exit horizontally polarized. If the photons entering are horizontally polarized, they exit vertically polarized. I invite you to pause this video now and think about how you can tell the difference between these 2 apparatuses if all you have access to is this output signal here. How can you know whether this is your input or this is your input? That's the riddle. Now, there are multiple ways to answer this riddle. I'm going to show you my way. My way is to turn down the intensity of the laser inputs. This interference pattern is a mirage. It is a mirage of macroscopic scale. This is not a quantum interference pattern. When the interference pattern here is occurring, because every second through both of these arms with standard intensities of lasers, billions upon billions of photons are coming in, and those individual wave packets from each side are interfering with other wave packets. This is a mirage, this interference pattern. If you turn down the intensity, the individual photons, so that you can see individual photons striking this plate, you will notice that individual photons do not interfere with themselves in this setup. There is no quantum interference. There is only the mirage of macroscopic interference. If you turn down the intensity here, you end up with photons striking, individual photons striking a plate in that pattern. Here, in this setup, you get quantum interference. Each individual photon that exits this laser through its wave function travels both arms and interferes with itself before striking this plate. This experimental setup allows for quantum interference. And when you turn down the intensity of the laser enough, you will see a quantum interference pattern. Thank you for listening to my riddle and the answer. So, now, the measuring device. What is the measuring device? Well, it is basically the riddle that we have just gone over. This is the measuring device here. Very similar to this part of the riddle. It is a true quantum interference device. This is this. So photons on this arm enter this polarizing beam splitting prism, go to two mirrors, one arm, so here horizontal photons are going, the horizontal portion of the wave function is going this way. The vertically polarized portion of the wave function is going this way, entering a half-wave plate, being rotated so that striking this knife-edge mirror are two streams of horizontally polarized photons, and then going down here, traveling, forming an interference pattern here. So here is the situation. If we measure this arm first, we know with 100% certainty that whatever arm the photon comes out here, let me restate this. This polarizing beam-splitting prism collapses the wave function, puts the photon pair into a determined state regarding its axis of polarization. The photons exit, and if it's horizontally polarized, it strikes this beam stop. If it's vertically oriented, it hits that beam stop. Regardless of which way it goes, we don't care. We just want to collapse the wave function of the partner arm at time 1 before it strikes this measuring device. So if the photon, which strikes this measuring device, is collapsed, it only travels one way. The wave function does not permit it to travel both arms. It is known with 100% certainty to be either horizontal or vertically polarized. If it's horizontally polarized, it will go this way and strike. Give this pattern. If it's vertically polarized, it will travel and strike and give this pattern. There is no quantum interference. It cannot, through the wave function, travel both paths because it has already been determined prior. This is what you receive, a non-interfering pattern of photon striking. Now if you measure at time 3, we have a different scenario. You could actually measure, not even measure, on this arm. Meaning that this is the arm that encounters the photons first. That means that striking this measuring device is a photon that is in a state of superposition. Its axis of polarization is undetermined. It is traveling as the wave function. It will strike this polarizing beam splitter prism, and through the wave function, since it is not yet collapsed, it will travel both arms. Each photon will travel both arms, and striking this mirror are two horizontally polarized beams, which will then travel down here and interfere. And when we look at the single photon pattern, it will show an interference pattern, because photons in a state of superposition that are not yet collapsed will travel both arms, and you will get quantum interference. So there is our signal. If you measure at time 1, you collapse the pair, you get a determined photon traveling through the measuring device, be it vertical or horizontally polarized. No quantum interference can occur, and you receive that pattern. If you measure at time 3, quantum interference can occur with the photons striking that device, and you receive this pattern. That is the signal